So I wrote here, another important voltage problem is the parallel plates problem. Typically, we draw it something like this here, okay? What we do is we have large flat metal plates. Now, by large, Tice, I don't mean a meter long. I mean large relative to those electrons and protons, like even a few centimeters long will work. The longer they are, though, the better they are. They're charged up using a power supply. You might recall from your Science 9 days, this is a symbol for a cell or a battery. And in fact, you might recall this is the positive end of a battery. This is the negative end of a battery in a circuit diagram. If not, we're doing circuits next unit, and you'll have these symbols down cold. And what you end up with is one end of the plate being positively charged, and one end of the plate is negatively charged, or it's charged to 0 and left grounded. Okay? So usually one plate labeled positive for a higher voltage is charged to a large positive voltage, and the other plate labeled negative for a lower voltage is left grounded. And if the metal plates are very large, and again, Lewis, by very large, I mean on the atomic scale, which means not all that large, half of a ruler length works, 15 centimeters works quite well. Then here is the key. The voltage, come on, pen. The voltage varies directly with the distance from the plates. Say, what? Show you what I mean. Let's imagine that we have plates separated by 5 millimeters, and they're charged to 500 volts. Ty, how many millimeters apart are they? How many volts are there? It means each millimeter that you travel, you're going through 100 volts. It's a nice linear relationship. So if I leave this grounded, so it's 0 volts, and I charge this or I hook this up to 500 volts, then if I go 1 millimeter, I've gone through 100 volts. If I go 2 millimeters, I've gone through 200 volts. If I go 3 millimeters, I've gone through. If I go 4 millimeters, I've gone through. If I go 5 millimeters, I go through. Okay? So that alone is nice. But the other thing that's really, 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 really nice, by the way, it says make a graph and find the slope. I'm not going to do that. I just want to use this picture. The other thing that's really nice is I have a constant electric field, not a changing Tamara electric field like with point charges. Because here's a charge. Don't write this down. Just watch. There's a charge. And let's make this charge negative. Okay? This down here is negative as well. Ty, is this plate, the bottom plate, attracting or repelling this negative charge? Repelling. As it goes further away, as it moves further away, what happens to this repelling force? It gets smaller. What about this plate up here? Is it positive or negative? Is it attracting or repelling? Not very much right now, but as it gets closer, what happens to the force of attraction? And so what you actually end up with in a nice linear relationship, as the repulsive force gets smaller, the attractive force gets bigger, the force itself is constant. The net force itself is constant, because when one goes up, the other one goes down. And because you have a constant force, you have a constant electric field. It's going to be really nice. Okay? So it says, make a graph, find us, blah, 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 blah. Here's what we're going to say. Between parallel plates, there is a constant ratio of voltage drop over distance. There is a constant ratio of voltage drop over distance. I'll put my little wings on there so you know that's a V for voltage and not velocity. And it turns out that ratio is the electric field. We'll put this equation in the box. This equation is on your formula sheet. This equation is the electric field, not between point charges, but between parallel plates. And the way I'm letting you know that these aren't circular point charges is I'm not using R, radius, for distance. I'm very deliberately using a D for distance. That's the clue on your formula sheet. Don't use this one for point charges. For circular charges, that's a radius. Use electric field that has a radius in it, KQ over R squared. So, it also means that the electric field is uniform. Electric fields point from what? Well, how do we figure out the direction of electric field? We ask ourselves a question. We ask,
If you put a proton, which way would it go?
I'll even say smaller than a proton, a positive charge, because even a positive charge so small, it doesn't have its own electric field and change the question. okay? Which means they always point from positive to. So if I wanted to show the electric field between plates, they would look something like this. What I want you to draw is to draw a series of equally spaced parallel lines like this. This would be a picture of the electric field between parallel plates, and try and make them equally spaced apart. You can eyeball it. The equal spacing, Lewis, tells you that the electric field is uniform. In other words, Lewis, if you did this, I would say, no, because remember I also said electric field lines, the closer they are, the stronger the field. You're saying the field is strong, right? No. It looks like that. This is the electric field between plates. Now, it blurs a bit at the end. There's a bit of a curvy one there and a bit of a curvy one there. And this is why old-style TVs could never get a nice, perfect picture. There's always some blurry, but it's close. It's close. It's close. So here's our equation. It's a scalar equation in that the direction comes from saying from positive to negative. Which way would a positive want to move if it could? We're going to insert the direction. The electric field between plates is the change in voltage divided by the distance between them. Where is the direction? From positive to negative. And D is the distance of the plate separation. Let's crunch some numbers. So here's a couple of plates, parallel plates. Looks like the left side is charged negative and the positive, and the right side is charged negative. It says find the electric field and direction inside the plates. So what does it want me to find, Jordan? I'm not going to use this, because R is when you have circular point charges. It's a radius. I'm going to use this one. Jordan, what is the change in voltage? The left-hand plate, how many volts is it? The right-hand plate, how many volts is it? What's the change in voltage? 225. You might once in a while see something like this, 325 and 100. Don't write that down. That's still a change in voltage of. And compared to the left side, the right side is more positive than the left, so a positive would still move that way. Isn't this positive? Yeah, but this is way positive. It's going to repel it still. Okay? Usually I'll give you 1 as 0, because typically we ground one of the plates. But just in case, don't, read the numbers. Okay? Sorry, what did you say, Jordan? Change voltage was what? And the distance is, careful, don't say 3, because it's 3 centimeters, 0.03. What's the uniform electric field between the plates? $750 volts. Sorry, 750, not volts. What do I measure electric field in? Up until now, it's been newtons per coulomb, but now there is a new way. Is that okay, Mac? Did I type it in wrong? Oh, you know what? I missed a 0. How about 7,500? That what you know what? I wasn't finished. Honest, I was going to write more. Yeah, I hadn't just finished writing my. Yeah. Sure, sorry. The electric field 7,500. Now we could say, don't write this down, newtons per coulomb, but new units, another set of units you can measure electric field in. Lewis, what do I measure voltage in? What do I measure distance in? Turns out that also works. Just like for gravitational field, meters per second squared when you wanted to treat it as an acceleration, or newtons per kilogram when you wanted to treat it as a gravitational field. There was 2 sets of units there. Turns out there's 2 sets of units here. If we wrote newtons per coulomb, would you mark that wrong? No, but I tend to use volts per meter if I use the equation that has volts and meters. I tend to use newtons per coulomb if I use the equation that has force and charge. direction? Don't write that down, just imagine it there. Which way would this is the direction for electric field, Mac, always. Which way would a positive sitting right there want to move if it could? To the right or east? I'll call it to the right. Away from the positive towards the negative. Okay. Example 3. How does the electric field at point X compare with... Okay, my bulb is getting on its... I want to limp the bulb through till the end of the year. I hope I can. My projector is flickering a bit. How does the electric field at point X compare with the electric field at point Y? You should know this because I've been ranting about this for the past 5 minutes. This is one of the things we like about parallel plates. I said the electric field is uniform. What's another way? What does the word uniform mean? Constant or the same. Okay? So you ready? First of all, let's calculate the entire electric field. The entire electric field is the change in voltage divided by the distance. Colin, from left to right, how many volts do you go through?
500.
Yep. What's the total distance?
5.
Can you please do the unit conversion in your head?
0.00.
0.05?
Something like that.
Yes? Thank you for making me feel better about my yeah. 0.05. And I get 10,000 volts per meter, or newtons per coulomb. Now, let's look at location X, and let's look at location Y. Well, we've already got the voltage at location Y. The electric field at location Y. There's the electric field at location Y. What's the electric field at location X? So if you want to, you can put a little Y there. The electric field at location X is going to be the voltage divided by the distance. Now, Ty, I'm going to come back to you because you were the one I asked about those millimeter questions at the beginning of this lesson, yes? How many volts all the way across? How many centimeters all the way across?
5.
So what's each centimeter worth in voltage? How many volts all the way across? 500. How many millimeters all the way across? So what was each millimeter worth in voltage? 100. How many centimeters all the way across? How many volts all the way across? What's each centimeter worth in voltage? In other words, from here to here, 2 centimeters, how many volts have I traveled through? Divided by 2 centimeters, because that's how far I've traveled. And it turns out here you also get 10,000 volts per meter. You want to travel a distance of 3 centimeters, it's going to be 300 volts divided by 3 centimeters, and you're going to get 10,000 volts per meter. So what's the electric field is the same, and if you want the proof, there it is. That fact is going to allow us to, Lewis, take a lot of shortcuts. If we know we're between parallel plates, you're going to notice in a couple of days our potential energy equation becomes much nicer. Our force equation becomes much nicer. This is also going to allow us, turns out, to explain lightning. What? Next lesson. Example 4. How does the electric field at point X compare with the electric field at point Y? Looking at these two situations, we've already answered situation A. We've said they are the same, uniform electric fields. What about, with me? Looking out there. You good? What about situation B? Situation B, is that a set of parallel plates or is that a point charge? It's a point charge, which means it's circular. You know what? I'm going to use the electric field equation that has an R in it. The electric field at point X is going to be KQ over Rx. It's going to be squared. I did the voltage equation there. I did the same thing. I told you it's easy to get all these equations mixed up. KQ over 0.02 squared. What about the electric field at point Y? I'm just going to do these algebraically and then quit. I'm not going to crunch this because I don't know what Q is. They haven't told me the charge. Well, the electric field at point Y is going to be KQ over 0.05 squared. Will those two give you the same answer? They can't. One, you're dividing by 0.02 squared. One, you're dividing by 0.05 squared. Hey, which one's going to give you a bigger answer, X or Y? You're dividing by a smaller number, you'll get a bigger answer. Okay. So, here's my answer. How do they compare? So between A, they are the same. Between B, the field decreases from X to Y. And there's my proof. Which is why between point charges, we often had to go final minus initial. We had to say, well, this was that whole principle of superposition where I said, ignore your first location, find the electric field at that location, find the electric field at this location, and then add them vectorially, or something like that. Okay. So how do I find the electric field between parallel plates? Like that. Voltage divided by the distance between them. By the way, let me go back to here for a second. You'll see, not in your homework, but on the big review, they'll often give you this distance as well, because if it's multiple choice, that's a way to give you a possible wrong answer. They'll tell you how long the plates are. You don't want that. It's how far apart the plates are. The closer they get, the stronger the electric field. Next page. A little technical comment. We can see why the electric field is constant inside the plates and why it varies with the distance if we graph voltage. For plates, the voltage varies directly. For point charges, the voltage gives you, it's a reciprocal graph. It's based on, this is based on y equals 1 over x, or this is just based on y equals x, technically negative x because you're getting smaller as you move to the negative, but here you get a lovely straight line slope. Here you get a lovely straight line slope. Here you're going to get a reciprocal slope. And turns out the electric field is the slope because slope is rise, v over run, d. That's the electric field, v over d. This is also, the slope of this is also the electric field. It's changing. Those of you that are in calculus, yes, it's a derivative. Another technical comment. For all the electricity concepts so far, force, field, and potential energy, I've made a connection to gravity to help us better understand the new idea. What would the gravitational analogy be for voltage? Voltage is sort of like how high you lift something. If I lift something up right here, compare that, same mass. Sorry for those of you watching on YouTube. Same mass. Which object has more potential energy? Which object has more energy per kilogram since they're the same mass? The higher one. Which object, which charge would have a higher voltage? Voltage is sort of, in my mind, I sort of treat it like height. It's actually more similar to height per kilogram, which isn't anything we do in energy, so it's not exactly like height, but when I solve circuits, or when I see a big voltage, what I imagine is, you've lifted the same rock higher if I'm comparing two charges in different voltages. So my analogy voltage is kind of like height. Kinda. Sorta. In fact, then you can think of the parallel plate, this one, as a hill with a steady slope. And you can think about this one as a hill that starts out really steep and then shallows out. Okay? The field, the electric field, is uniform in parallel plates, same voltage slope everywhere, and it changes around a point charge because the voltage slope changes as as we move away from the point charge. In terms of direction, remember, electric field is from a positive to a negative. It's which way would a positive want to move if it could. You know what? It's downhill, which is kind of nice in terms of our slope graphs. Short lesson, I told you. You know, I think because it was a short lesson, I'll give you the take-home quiz today because you have time to work on it as well. So, what's your homework? Number 1, number 2, number 3, number 4. In question number 4, let me just pause the video for 1 second. Donk. Let's keep going. In number 4, Jose, in number 4, what are they asking me to find?
Force.
What did they ask you to find in number 3?
The electric field.
I think what you can do is you can say if electric field is force divided by Coulomb, do you think you get the F by itself? This is also another, now I have a much quicker way to find the force because the electric field is really easy to find between parallel plates. It's going to be, Jordan, the change in voltage here is not 255. Since this is 35 volts, the change in voltage here I think is 220 times or divided by that distance in meters. There's your electric field, bada bing, bada boom, right? It's much faster. So anyways, number 4. Number 5, Jose, what does number 5 want me to find? Work is going to be the change in potential energy, which is going to be Q, change in voltage. Oh, the change in voltage is 220. Q is the charge, 2.35 millicoulombs. So much shorter. Number 6, this is very similar, Jake, to the question you asked me earlier. Find the electric field north of an electron. Now we're a point charge. Now I'm going to have to use the one with the R in it. Okay? I'll pass on 7. I'll pass on 8. Oh, this is all review. Boy, we need to start doing some review, but I'll skip that for now. So we're going to go like this. And I have a